because digital circuits didn't really exist at that particular moment. As you are already aware, Boolean algebra relies on the fact that there's really only two values in a particular system. True, false, or you might see them represented as 0 and 1 in this particular case, since we're interested in the binary system. And the operators involved with Boolean algebra, there's really only three that are necessary: and, or, and not, which I'm sure you're already familiar with through your programming experience using Java or some other programming language. With those three operators, we can actually specify any logic that we could ever possibly conceive of, whether that be in a digital circuit or otherwise, in a purely mathematical sense. So those three operators are really the only ones that are necessary. In fact, I think you can get away with even fewer than that. But there are additional operators as part of Boolean algebra that will be introduced as time goes on to make things a little bit easier for us to discuss certain problems and situations. So be on the lookout for those. Okay, the last thing I want to touch on in this very quick video is how to evaluate Boolean expressions. Again, you probably already had some practice doing this in your previous computer science courses, but it's good to mention it now since we're on the topic. The biggest thing is to pay attention to the order of operations. So here you see a Boolean expression represented as a series of ones and zeros, right? And so I have ampersands in here to represent and. Typically, and is represented by multiplication, so it could be, the multiplication sign, or just putting the numbers up against each other. I use ampersands here just to make it explicitly clear what I was talking about, so we didn't get confused by the arithmetic operations. But 1 represents true in this particular case, and 0 represents false. And so, in order of operations as it applies to Boolean expressions, not always happens before ands and ors. And then we also have to worry about the grouping of parentheses. So in this particular expression, the first thing that would happen would be knotting this 1 that we see here. So that effectively turns it into a 0. And then we would evaluate the stuff inside of these two smaller parentheses. Actually, it looks like I'm missing a parenthesis on the end here. Whoops. Anyhow, so 1 or 0 is going to be 1. That's a true statement. And then I'm going to apply this not to that particular value, which turns this entire expression here inside this first set of parentheses into a 0. Over here, I then evaluate what's inside of these parentheses, right? 0 and 1 is going to be 0. They both have to be true. They both have to be 1s in order for this to evaluate to be 1. So we have 0 or 0, which is going to be 0, right? And then over here we see 1 ANDed with that 0, which is going to be 0 as well, which means this whole entire expression here evaluates to be a 0. So the big takeaway here is pay attention to order of operations. Not takes precedence over ands and ors, and you can use parentheses if you would like to help group things together to make your expressions more clear. In the next video, we'll talk a little bit more about the history of Boolean logic as it applies to digital circuits. And then we'll talk a little bit more about creating circuits after that. So in this video, I want to talk to you very briefly about Boolean logic as it applies to designing digital circuits. This idea really came about thanks to this man, Claude Shannon, back in the 1930s and 40s. He is actually the founder, considered the founder of information theory, which is a precursor, of course, to computer science as we know it. What Claude Shannon did was he took Boolean algebra, which had already existed for many years by the time he came around, and he applied it to his electrical engineering background, his digital circuits background. In fact, he even took it a step farther. He proved that Boolean algebra can construct any logical or numerical relationship. And so what that means is it allows us to use Boolean algebra as a tool to talk about digital circuits. So if we want to build a circuit, for example, we can actually boil that circuit down to a Boolean algebra expression or a Boolean algebra equation. In fact, since we're on that particular topic, now is a good time to cover some terms. So an expression, a Boolean algebra expression, has no equal sign. It's simply a series of inputs to a particular circuit, for example. So you might see ands, ors, and nots and other operators, but the variables involved are always going to be inputs if it's an expression, and there will not be an equal sign. An equation, on the other hand, will include an equal sign. And so that represents inputs and outputs, which is very useful when we're talking about circuits. If we want our circuit to have a desired behavior, it's going to have inputs and outputs, more than likely. So an equation defines both inputs and outputs, and it has an equal sign. A function, on the other hand, describes a relationship between the inputs and outputs. And so functions can be represented in many different ways. One of those ways is actually equations. So I can represent a function as an equation. Another way that we've already seen a little bit of, and we're going to see a lot more of in the future, is a table, a truth table specifically. A truth table defines a function between inputs and outputs. And of course, another way that we can define functions is as a physical circuit itself. A circuit, a physical circuit, represents a Boolean algebra function between its inputs and outputs. So functions are going to be increasingly important as we proceed, not just with Boolean algebra, but also with building circuits in this particular class. In the next video, we're going to take a deeper look at building circuits and drawing circuits so that we can prepare ourselves to have a more thorough conversation about Boolean algebra and designing circuits using VHDL. So in this video, I want to go over some common conventions when it comes to creating circuits. This is going to be important for basically all of your homework assignments, and so it's a good thing to talk about this kind of stuff early so that you get in good habits early. So when creating circuits, there's a few general rules of thumb that you should follow. If you truly want wires to be considered connected in your circuit, you should indicate that by putting a little dot that indicates that those wires are in fact connected. If wires just simply cross over one another, it's convention to consider those wires not connected. And so it's often the case where we're going to have lots of wires involved, and they're going to have to cross paths at some point. It's very important to make the distinction between whether those wires are crossed, or whether those wires are actually connected, or whether they're just passing over one another. Some other important conventions. If you ever have inversions happening, you don't necessarily have to draw the entire NOT gate. You can oftentimes represent an inversion by simply drawing a little circle instead. So you'll see this happen quite frequently in logic circuits. In fact, we're going to see that happen a lot more as we start introducing more and more types of components into our logic circuits. So it's good to get used to that habit now. When it comes to splitting your wires, it's always acceptable to split things coming out of the output of a particular logic gate. Splitting things going into a logic gate is not a good thing. In fact, in this particular case, we see a 2-input AND gate that's actually connected to 3 inputs, which is very confusing and not really possible in this particular case. So another thing to pay attention to that was kind of in all 3 of these first examples is labeling your inputs. If you have inputs that you don't know what the values are, they're variables, in other words, they could be either true or false, you should label them traditionally with letters, right? Starting at the beginning of the alphabet. Your outputs can also be labeled as well. You see here in this particular example, they've labeled the output of this AND gate as an equation. We see the equal sign in there that indicates that this is an equation. It's not absolutely necessary to put the entire equation as part of your output. It is good practice, but not entirely necessary. You can label these as individual letters as well. Typically, the outputs will start towards the end of the alphabet. So we'll use X, Y, and Z to represent outputs, A, B, C, D, etc. to represent inputs to our logic circuits. If it makes sense to duplicate your input labels, if you have an input going into multiple gates, and it's cleaner to have two labels for the same input, that's actually a good thing. Don't feel like you can only have an input at one particular point in your circuit, especially if it's an input that's used frequently. That will actually probably make things messier than if you just create the same input label in multiple locations like we see in this particular example. And the final thing that I actually see students do quite often, which is not necessary and makes things confusing, to be perfectly honest, is labeling the inputs and outputs of the gates. You should typically not label gate inputs and outputs. So here you see this AND gate was labeled. That's actually a bad practice. Labeling the inputs to a circuit is perfectly fine, and that's whenever you see letters on a schematic, that's typically what they refer to is inputs and outputs for the entire circuit. Doing that on the individual gate level is not necessary and will only make things confusing. Now there is an exception to that we're not going to see right away, but we will see eventually as we start developing more complex circuits. Sometimes we'll have things that aren't gates, but they're actually components. They're modules. And these modules will have, their own sets of inputs and outputs. If you see a component or a module, typically represented by a rectangle, a box, it is okay to label those inputs and outputs. In fact, you probably should label those inputs and outputs. So do it for custom components, do it for customized modules. Don't worry about labeling the inputs and outputs of each individual logic gate. That is unnecessary. The next thing I want to talk to you about in terms of drawing circuits is a couple of the symbol guidelines that I'd like for you to use on the homework assignments. So we're going to be seeing transistors a lot, at least at first. And so when it comes to including transistors in your circuits, I actually really prefer the forms that you see here on the left. You see I've got the NMOS and PMOS transistors. The distinguishing feature here is this circle on the gate of the PMOS transistor. These are the simplest ways of representing these transistors. Entirely sufficient. You do not need to include the labels for the gate, the source, and the drain. That's not required. Just the symbol itself is fine, right? And so if you're drawing these things out by hand, this is probably the easiest way to do it. If you're using a computer tool to draw circuits, which actually I've included a link on this particular section to some circuit drawing utilities, you probably won't see these symbols. These symbols are often not included in professional circuit drawing packages. So you probably won't see these symbols if you're designing circuits on the computer. You're more likely to see symbols that look like this, and I would prefer if you have the option to use these symbols to represent NMOS and PMOS transistors if you're using the computer to design your particular circuits. It's good for us to keep things consistent so that I don't have to guess whether you mean an NMOS or a PMOS transistor there, so that it's entirely clear which one you're actually intending to use. So that's the deal when it comes to transistors. The other thing that I wanted to point out are some input and output symbols. So in schematics, it's common for input and output to inputting a positive value, for inputting a high level of voltage, it's common to use VDD. And so the way that you do that typically is to just simply write VDD, and then you have this T symbol that's used to input a high level of voltage. Now what the actual voltage is not particularly important, right? It could be 5 volts, it could be 3 volts. We just accept it to be a high level of voltage. To represent a low level of voltage on a schematic, we'll typically use the ground symbol that you see here. Right? This may also be represented as just an empty triangle. That's okay too. This is the traditional ground symbol. This is used to represent a low signal within a circuit. Alternatively, you may, in some cases, just use a simple 1 or a 0 if you want to input high or low values. That's okay too. Right? So these are more sort of electrically focused, the VDD and ground symbols. These are more logic focused, 1 and 0. Either one is okay for the perspective of the homework. But basically, it does need to be clear whether you're talking about high or low signals within a particular circuit. Now, not all circuits will require this, so don't feel like you need to include these symbols in every circuit you draw. Sometimes we're going to have variable inputs, so we don't know if they're going to be a 1 or a 0, or they could be both at different times. right? But if you know absolutely that you need a high or a low signal, then these are the symbols that you should use to represent those particular signals. You are going to see this, like I said, on the homework assignments and the exams. So if you have any questions about these particular symbols or how to use them or how to create good schematics, please don't hesitate to ask in class or on Piazza.